Most chemical reactions do not occur in a single step, so a reaction mechanism is the series of individual steps by which an overall chemical reaction occurs. The decomposition of ozone to oxygen is proposed to occur by two elementary steps. Step 1, which occurs fast and in equilibrium due to the reversible arrow, is unimolecular because there is only one reactant involved. Step 2, the slow step, is bimolecular because there are two reactants involved. The slow step in the reaction mechanism is the rate determining step. To prove that a proposed reaction mechanism is consistent with an experimentally derived rate law, we must satisfy two conditions. First, the elementary steps of the reaction mechanism must sum to the overall reaction. And second, the rate law predicted by the mechanism has to be consistent with the experimentally derived rate law. Let's add the steps of the reaction mechanism to find the overall reaction. Remember that when adding reactions, all species on the left side of the arrows stay on the left, and all species on the right side of the arrows stay on the right. I can cancel out species that occur on both sides and combine like terms. The steps of the reaction mechanism do indeed sum to the overall reaction, and so the first condition is met. Notice that oxygen is produced in step 1 and consumed in step 2, therefore canceling out. That is called an intermediate, which will be important for us when deriving the rate law. Now we must derive the rate law from the reaction mechanism. Since step 2 is the rate determining step, we will write the rate law based on this step. A couple of things to note. I added the subscript 2 on the rate constant just to indicate that it came from step 2. And most importantly, notice that there is an intermediate in our rate law. This is a problem. Since reaction intermediates do not appear in the overall reaction equation, we cannot have a rate law where an intermediate is present. So we must use some algebra to remove the intermediate by expressing it in terms of the concentrations of reactants in the overall reaction. To remove the intermediate, we will start by looking at the fast step in the reaction mechanism. This fast step is in equilibrium, which means that the rate of the forward reaction is equal to the rate of the reverse reaction. The rate of the forward reaction is equal to K1, and again I'm calling it K1 because it is coming from step 1 times the concentration of O3, and the rate of the reverse reaction is K minus 1, using minus 1 to show it's the rate of the reverse reaction in step 1 times the concentration of O2 times the concentration of O. Since the rate of the forward is equal to the rate of the reverse, I can set these two expressions equal to one another and solve for the concentration of O, which is the intermediate. Now I can substitute the concentration of O into the rate law predicted by the slow step. I have now expressed the concentration of the intermediate in terms of reactant concentrations in the overall reaction. I can combine like terms, and I can also combine all the rate constants into one overall rate constant and call it K. So my rate is equal to K times the concentration of O3 squared times the concentration of O2 raised to the minus 1. Notice that this rate law that we have derived from the reaction mechanism is consistent with the rate law that was experimentally derived, and therefore we have satisfied condition number 2. The proposed reaction mechanism is consistent with the experimentally derived rate law.